In this video, we are going to see how the motor is converting electrical energy to mechanical energy. And finally, from the obtained mechanical energy, that is from the mechanical force, we have to see the direction and we have to verify the direction with the Fleming left-hand rule. For that, we will see the working principle. That is the working principle of motor is whenever a current carrying conductor placed in a magnetic field, it experiences a mechanical force. So from this we can conclude one thing, that is we have to place a current carrying conductor in the magnetic field. At the time that current carrying conductor, it's going to rotate, okay, because of that mechanical effect. So the mechanical effect is the output and we are giving input as the current to the conductor, and along with that we need to provide some magnetic field system. Okay, so we have to explain it, we will see the diagram. Let us see this diagram. In this diagram I have taken singleton coil. This coil is energized by a DC supply. Through the brush and commutator segment I am giving the supply. So current is flowing likewise and it will flow through this conductor, it will flow in inward direction, and here it will follow the outward direction. The meaning is this conductor will carry the inward current and this conductor will carry the outward current. Okay, I am keeping this entire setup in the magnetic flux path. So this pole are going to provide the magnetic flux. From north to south the flux lines are moving. I am placing this setup, okay, in between it. And already we know the basic thing, in any current carrying conductor, around it we have we can able to identify the flux. So here also state conductor is there. We are sending the current through this path, and here from this conductor current is coming out. So anyway current is passing through these two conductors, so around it some flux going to be induced, right? And to refer the direction of magnetic flux and the direction of current, we can take two methods. One is Maxwell right hand thumb rule and another one is Maxwell corkscrew rule to identify the direction of magnetic flux and the direction of current in the conductor. Okay, so for that the first method is Maxwell right hand thumb rule. Here, so you have to assume this is the conductor, okay, this is the conductor. Now the current is flowing from this end to this end. So this is the current flow direction. Current is flowing inward to this conductor. So now I am holding this conductor likewise. According to right hand thumb rule, we can say here this is the straight conductor. So this thumb will point the direction of current in this conductor, and the remaining finger shows the direction of the induced flux around this conductor. Okay, and also we can see the direction. The direction of this remaining finger is following a clockwise direction around this conductor. So the meaning is in this conductor, this conductor carries inward current. So the induced flux around this conductor is following clockwise direction. Okay, according to the first method, right hand thumb rule. And I am going to apply the same method for the second conductor also. This will carry the outward current. So outward means the current is coming out. So I am going to keep my hand like this. Okay, so the current is coming out from the conductor. Okay, the current is coming out from the conductor. Now my thumb is pointing the current direction, and the remaining finger is going to represent the flux which is developed around this conductor in counterclockwise. Okay, in counterclockwise. So the outward conductor means counterclockwise, and the inward conductor carry the clockwise direction of magnetic field. So this is what we have observed from the first method. And second method is corkscrew rule. That is, generally we know in any hole, if you are inserting the screw in that hole, we need to drive that screw in clockwise. Then only that screw will go inside the hole, right? If you want to insert this hole in any hole, if you want to insert the screw in any hole, we need to drive this screw in clockwise direction, then only it will go inside. Okay, so this, and if we want to take the screw from the hole, we need to drive in opposite direction, that is counterclockwise direction. So if we are driving it in counterclockwise direction, it will come out. Okay, so same concept we are following in the second method. That's why that name was corkscrew method. Okay, so in inward means clockwise direction it should rotate, and the outward means it should rotate in counterclockwise. To drive the current, we need to rotate the screw in clockwise direction for this conductor. So in this side the current is outward, so to drive it to taking out the screw, we need to rotate in counterclockwise. So counterclockwise means that it shows the direction of the developed flux. Okay, see, this is the cross-sectional view of the conductor. The first conductor is representing the inward current direction, and the second conductor representing the outward current direction. The meaning is, inward means we have to see the screw, so it is the current is going inward. Okay, now we can able to see this face only, right? So this is like star symbol, right? So that is why we are taking inward means star symbol. And from this conductor the current is coming out, right? Current is coming out. So coming out means we can able to see the tip. So that is why we are representing the dot. Okay, for the outward direction of current we are taking dot. Now in the inward, the conductor carries the magnetic flux which is flowing in clockwise direction. That's what we were verified by using the two method. One is Maxwell right hand thumb rule, and another one is Maxwell's corkscrew rule. Okay, and here this conductor carries outward current, and the developed flux is rotating in counterclockwise direction. Okay, now we have to see these parallel lines, no, that is nothing but main flux phi m. It is flowing likewise, and this conductor, that flux is, I am naming it as phi c, that is flux due to the current carrying conductor, that is phi c. Now I am comparing these two flux in the top of the first conductor. So in the first conductor top portion we have several flux, main flux are going, and the developed flux also there. So while comparing these two are in the same direction, so both of them aid with each other, hence the net flux will be high. Okay, net flux will be high. And in the bottom of the first conductor, the main flux are flowing likewise, and the phi c is moving in opposite direction. So both the fluxes are opposing nature, hence net flux will be low. Okay, and in the second conductor you have to see this is the main flux direction and this is the phi c, both of them opposing nature, so net flux will be less. Okay, low. And in the bottom of the second conductor, the same conductor, we have to see both the fluxes are, main flux are moving this direction, and the phi c also moving in the same direction in this portion, particularly in this portion. So the net flux will be more, both of them going to aid, so net flux will be high. So always high flux density will try to move the conductor from higher flux portion to lower flux portion. So here in the top of the conductor we have more flux strength. That flux strength will move the conductor towards the lower flux strength. Hence this conductor will get the motion in downward direction. And the second conductor, flux density will be more here and flux strength is less here. This higher strength will move the conductor in towards the lower flux strength. So hence this conductor getting motion in upward direction. So if you are giving continuously the supply to this conductor across this conductor, then this conductor will come to this side and this conductor will go to this side. So finally both the conductor will make a rotation that is in counterclockwise direction. Okay, it is going to rotate in counterclockwise direction. So that's what we are getting here. We are giving only electrical energy across the conductor. Finally the conductor getting the motion. Okay. So the mechanic, by this way the motor is converting electrical energy to mechanical energy. Next we have to see the obtained that motion in the first conductor is downward, the second conductor is upward. We have to verify this motion with the Fleming left hand rule. Okay, Fleming left hand rule, we can verify the direction of all the quantity. Now in this figure we have to see the Fleming left hand rule. In the Fleming left hand rule, I am taking three fingers, okay, thumb, forefinger, middle finger. All of them should be in perpendicular. Middle finger should show the direction of current, and it should show the direction of magnetic flux, and the thumb should show the direction of motion. Okay, and we know the magnetic flux and the current is input of the motor and the motion is output. Okay, the magnetic flux is flowing from north to south, so I am going to keep the forefinger in this direction. So it show the direction of main flux which is flowing from north to south. So that's why I am keeping my forefinger likewise. And my my middle finger, it is also the input signal, that is current. Current is inward direction for the first conductor. So I am going to just turn my hand likewise, and my middle finger should show the current direction. Current is inward, so I am keeping likewise. Okay, so this is the current direction of conductor. So that's why I am keeping my middle finger likewise, and the forefinger is pointing the main flux direction, and this is my thumb. It should show the direction of motion. Yes, it's showing in downward. Okay, as per the 90-degree displacement with each finger, my thumb is pointing downward, right? Downward. Hence, according to the flux density concept, my conductor was driven in downward direction only, the first conductor. So according to Fleming left hand rule also, I am getting the same motion. So it is verified. Okay, and in the second conductor you have to see, according to the magnetic flux concept, the conductor was driven in upward direction. We have to verify this with the Fleming again left hand rule. So I have to keep like this. Okay, my middle finger coming out, that is from the conductor current is coming. Okay, so that is why I am keeping my middle finger like this direction, and this is my forefinger. It should show the direction of main field flux. Yeah, main field flux is flowing likewise, so that is why this arrow is likewise. So I am keeping my forefinger in the same direction, and according to this position, my thumb is pointing upward. This means the motion should be in upward. As per this position, the corresponding conductor should move in upward direction. Hence, my conductor should move in upward direction. So that is what is verified here. Thank you for watching this video.